Hello everyone, my name is Hunjun Lee and I'm from Seoul National University. In this talk, I'm going to present NeuroEngine, a hardware-based event-driven simulation system for advanced brain-inspired computing. This work was done with my fellow students and my advisor, Professor Jang-Ho Kim. Let me start with a brief introduction of the spiking neural network. Spiking neural network, namely SNN, models the mechanism of the brain and emerges as a representative brain-inspired computing method. Each neuron keeps a time-varying state called voltage which changes with both incoming spikes and time. There are two representative simulation methods of the SNNs called the time-driven simulation and the event-driven simulation. The time-driven simulation calculates the voltage change of a neuron every time step of the simulation and thus it incurs excessive computation overhead. For each computation, the voltage changes with respect to the incoming spikes. And also, the neuron fires an output spike if the voltage exceeds the threshold. On the other hand, the event-driven simulation method computes only for each event. Each event is scheduled as a result of the weight accumulation, which transfers spikes to the destination neurons. For each event, it calculates the aggregated voltage change over multiple time steps at once. It also predicts the next output spike for each computation and schedules a new event so that it performs computation when the neuron fires a spike. Like this. Then, we profile how many computations can be skipped using the event-driven method. And the result shows that the event-driven simulation requires 8.54 times less neuron computation over the time-driven simulation. And thus, it is a highly promising solution. However, in reality, the event-driven simulation is much slower despite its high potential. Our evaluation using the baseline event-driven simulator shows that it achieves only 0.58 times simulation speed compared to the time-driven simulator. We identified three challenges that slow down the event-driven simulator. First, it involves complex computations and thus, each computation incurs high operation cost. Second, some events interact and invalidate each other. Therefore, the simulator cannot fully reduce the number of computations when such interactions are not handled properly. Lastly, both neuron computation and weight accumulation schedules an event using an event queue. Therefore, the simulator suffers from the resource contention when parallelizing them. To solve the challenge, we propose three key ideas. To minimize the per operation cost, we divide the computation into three parts and devise a pipeline ASIC-based data path. Then, we devise a custom event queue called composite queue. It has auxiliary data structures to detect invalid events. If the invalidation is detected, the queue removes the invalidated event and schedules a new event. And therefore, the composite queue keeps only valid events. Lastly, we devise a lazy update method to maximize the parallelism. Our key idea is to parallelize neuron computations with weight accumulation, which transfers spikes to the destination neurons. We observed that some neuron computations can be deferred without the need to schedule an event, and NeuroEngine keeps such computations in a separate buffer. If a neuron is expected to fire a spike, it flushes the deferred computations to the lazy queue. Then, NeuroEngine parallelizes the computations in the lazy queue while performing weight accumulations. Although the weight accumulation schedules a new event, it does not incur resource contention as the deferred computations do not incur event scheduling. And thus, we achieve high parallelism. We combine the three optimization schemes to design a single NeuroEngine core and maximize the benefits of the event-driven simulation. Using the three optimization schemes, NeuroEngine significantly improves the performance. The result shows that NeuroEngine achieves 7.38 times speedup over the baseline event-driven simulator. It also achieved 4.3 times higher speed over the time-driven simulator. And thank you for listening. And now I'm more than happy to answer your questions.